Please, we can start.
Okay. Yeah, so today's topic is practical cryptography in Ethereum. We won't go too deep into the cryptography, into the formulas and the proofs of those formulas, because it is like the topic of a different course. Today we are going to discuss the practical side of the cryptography and how Ethereum leverages it to operate and what you can do with the available like functions and how to use them. Yeah, so if you have any questions, just type them in the chat. I'll answer them right away. Okay, so let's start with the definition. The cryptography is a branch of mathematics that ensures the confidentiality and authenticity of information. Yeah, so basically, it is needed to make this information, first of all, confidential, that you can prove that something belongs to someone, and the authenticity is that you can just change the information itself, and there is a way to prove it. Ethereum's foundational technology. So cryptography lies in Ethereum roots, and it makes up a really decent part of its operability, because Ethereum highly uses hash functions, public key cryptography, mostly like digital signatures from this public key cryptography. And it is like used pretty much everywhere. Ethereum uses it to control users' funds. So addresses of the users and private keys of the users are utilized like cryptographically, and also everything that Ethereum maintains, its state, the transactions, the blocks, and like transaction hashes, pretty much everything is also related to the cryptography and hash functions. And yeah, because Ethereum is a blockchain, and usually blockchain is like highly related and associated with cryptography. So these two worlds like intersect and interact like really a lot. So what is a hash function? A hash function is a special function that converts an array of input data of an arbitrary length into an output bit string of fixed length, which is performed using a certain algorithm. So basically what it means is that hash function is a special thing, like special function that accepts arbitrary data, and it converts this data into the fixed like fixed length string that basically consists of raw bytes. And usually this string represents the input. And for a good hash function, it should be like collision resistant, and it should be hard to find the first image and the second image of the function. The first image is the one that's output. The second image is like the original input. It should be really hard to brute force the function to find the correlation between those two. And yeah, hash function is a kind of so-called trapdoor functions when it is easy to calculate its outputs one way, but it is really hard to like calculate it the other way. Yeah, this is about the definition. And which hash functions Ethereum actually uses. The major one is Cache 256, which belongs to the SHA-3 family, which usually is confused with the actual SHA-3 256 hash function, but it is a bit different from that one, because SHA-3, like the one that like was proposed, is a bit different because the implementation was settled like a bit later than Ethereum launched, and that is why Ethereum uses a bit different hash function called cache256, which like is a tiny bit different from the original SHA-3. And this hash function used pretty much everywhere in the platform. It is used in the like construction of addresses, construction of transaction hashes, construction of block hashes, and also the whole like set of algorithms that maintain Ethereum state also use this hash function to like combine the states in the Merkle Patricia state tree, and not only this tree, but pretty much every tree that is used in the state like maintenance algorithms. Cache256 is directly available via EVM. There is an like opcode that can be used by the smart contract to directly call this hash function, and it is relatively cheap. Also, Ethereum supports SHA-256 from SHA-2 family, but this hash function is only available as a precompile at address 2. So a bit of precompiles. What are they? These are special smart contracts that come with EVM, but they are not like directly EVM. They are the contracts that are built on top of EVM, but they like use EVM. And these contracts are deployed whenever they're first interacted. So when you, for example, set up a fresh blockchain, those precompiles won't be available straight away. But as soon as you call this precompile, the node will understand that the contract is missing, and it will deploy it. So there are, I think, 8 precompiled contracts right now in Ethereum, and the one that realizes SHA-256 is available at address 2. Yeah. And of course, it is already deployed on Ethereum mainnet and Ethereum testnet. And it works by basically hashing everything that you provided. So you can call this contract from your smart contract and set anything you like at the call data, and it will return the hash of this call data in the return data. Yeah, there is another hash function that is available as the precompile at address 3, which is ripenD 160. Just another hash function that's available as another precompile, but it works exactly the same as the SHA-256 precompile. So it hashes everything that you feed it. Also, it can be used by your smart contracts, like anytime you want. Yeah, starting with the public key cryptography, let's first of all define what is a cryptographic key. A cryptographic key is a digital sequence of a certain length created according to certain rules using random or pseudo-random number generators and are calculated according to a special algorithm from other values. So basically, it is just a sequence of bytes that follow like a certain generator algorithm, which usually uses random. And this string of bytes, because it follows the rules of the algorithm, contains a lot of like mathematical properties that are utilized by other algorithms, which makes those values really useful. And an example of the cryptographic key is the private key, your private key of the account that you use to send transactions in Ethereum. So speaking of public key cryptography in Ethereum, Ethereum uses elliptic curve public key cryptography. So this is the plot of the elliptic curve that Ethereum uses. Is actually the this one, the same that Bitcoin uses. It's just the name of this elliptic curve. And yeah, according to the rules of the like public key cryptography that Ethereum uses, every external loan account is like has a private key. So what I mean here is every user that Ethereum has, every externally owned account the Ethereum has its own private key. And there is a relation between the private key of the account and the public key of the account that is used to actually identify the account. And when, for example, the user sends a transaction, we'll talk about it in a couple of slides later. This transaction gets signed by a special signature algorithm by this private key. And because this private key is only known to the user, you can be sure that no one else is sending the transaction other than this user. And that is how like Ethereum identifies who sends the transaction and from whom to subtract the funds. The key point is that smart contracts do not have private keys. So they have the addresses, but these addresses are not backed by the private keys. And actually, it is kind of impossible to find such private key that would relate to the address of the smart contract. And also, usually when you're set up in a wallet, you will be provided a seed phrase. And usually users relate the seed phrase to some kind of password for the wallet. But actually it is like sort of correct, but technically not, because the seed phrase is just an entropy that is provided to a special generator that then produces private keys for your account. And seed phrase is just built this way. So there is a list of, I believe, 2048 English words, and the wallet just randomly chooses those words. And so in Ethereum, the seed phrase is a 12 words long phrase, but the first 11 ones are actually the the ones that represent the entropy, and the 12th one is sort of like hash of the first 11 ones. And those words are taken from a special dictionary. And when this phrase is fed to the generator, it just like rolls back those words and understands the bits of this phrase, and then using these bits, it generates private keys. And English words were chosen instead of like random string of bytes, because if there is a typo in any of those words, it is really easy to understand what's wrong, and yeah, it's more human readable. Okay, let me just quickly check the chat. If we have a private key, does it mean we have a public key? If so, who stores that public key? Yeah, so of course, if you have a private key, it means that you have a public key. So who stores the public key? So your wallet stores a private key, usually in an encrypted form. So for example, if you are using MetaMask, once you set up this wallet, it asks you to stab a password as well. And it uses your password to encrypt the private key so it doesn't leak anywhere. And public key may be like constructed from the private key according to some algorithm. And usually your wallet stores not the public key, but the address that can be constructed from the public key. And this process of construction we'll cover in like 2 slides, maybe 1 slide. Yeah, so I believe wallets usually don't store the public keys because they store the addresses. So you could receive the funds and understand like your account, because Ethereum uses the addresses to identify your accounts. And if you use, for example, Etherscan to check the balances, you will use your address, not the public key. Yeah, okay. Yeah, so here is it. Here is this. What is Ethereum external account address? So this is the process of address generation for externally owned accounts, because for smart contracts, the address generation is different. So number 1, generate a private key K. This is is made with a special algorithm that heavily relies on the random. And random here should be a well-made random, because if you're able to somehow trick the random generator, you'll be able to compute the private key for the public key. And this actually happened to many wallets that used a special software that would generate addresses with leading zeros. So yeah, usually this process is made by listening to some space noises, or mouse cursor hovering or something like that, that is pretty random. And the private key generation is done on the local computer itself. Point number 2. Multiply k by the elliptic curve generates for point G to get the public key bk. So this is the like usual process of public key generation using elliptic curves. So you have some publicly known point G, which is also defined for Ethereum, and it is like a huge number, like 60 symbols. Order, and you multiply this G point by itself k number of times, which also like a huge, like not multiply, but add this point to itself k number of times, which is also a huge number. And because of the elliptic curve properties, which is also the multiplication is the trapdoor function that you can easily like multiply numbers and understand that multiplying this by that gives you bk, but it is pretty much impossible to understand what have you done. So to get this bk number. All in all, you have the public key bk, and then what you do. And bk is the elliptic curve point, and points have like points on the plane have 2 coordinates, x and y. So you can concatenate those coordinates. So you represent those points as strings and just concatenate them. And then you calculate the cache 256 hash of this concatenation. This gives you the 32 bytes long string, or 256 bits long string. And then you take the least or the rightmost 20 bytes of this hash. So, and those 20 bytes are your address. So, and this actually like sort of proves that from your private key, you can receive your address. But this process like takes really long, and your wallets usually like store both the private key and your address to just skip those steps. And point number 6, there is an abstraction or your address, and that this address may be hidden or represented by an ENS name. ENS is Ethereum name service. So like DNS, the domain name service, but Ethereum name service. It is an amazing protocol that a lot of wallets support, a lot of applications support. It is basically a protocol that has special smart contracts deployed on Ethereum, where and those smart contracts track and sell names that are linked to your address. So basically, this is like your Ethereum domain. And we have like .com, .com, something. In Ethereum, we have .eth. And anyone can buy the available names and link them to the addresses and send and remember where to send funds, not by the 20 byte address, which is like impossible to remember, but send funds to the represented ENS name, which will be just a regular name. So it is super convenient. Yeah, just checking the chat. So public key and public address are two different things. Yes, they are. Why can't we just use public address, probably public key as the wallet address? We can, but it is just an optimization because those addresses are used everywhere, and like using them everywhere would just add the overload of 12 additional bytes, and probably this will consume more storage than needed. And developers of Ethereum thought that 20 bytes are enough, but for optimization, they just use it like this. EZNA is basically a huge hash map, or is more complicated than that? ENS is more complicated than that because there are like subdomains. You can have like topmost domain that is linked to your address, but then you can also have subdomains that are linked to other addresses, and etc. etc. Has a hierarchical structure, and you're also like buying this ENS not like for not forever, but you're like renting the name for like fixed period of time. So for 1 year, 10 years, and once this period expires, you have to renew it like again. EZNS connected to Tornado protocol. So in terms of does Tornado use ENS? Yes, it does, because they also bought ENS names for their contracts. For example, their DAO, I believe, use the ENS name, so users would understand that it is the real DAO, and they won't need to remember like the huge 20-byte string. But yeah, in terms of money laundering, of course not. They are not connected. What about the ENS security? It is as secure as it gets. It is one of the oldest protocols Ethereum seen, and it works amazingly. And yeah, it is super secure in terms of the protocol. But in terms of the integration of the protocol, it depends on the integration. Okay, so next part. What is a digital signature? A digital signature is an analog of a handwritten signature that provides two properties: the ability to verify the authenticity and integrity of the document, which protects it from modification and substitution. So, in other words, the digital signature is an analog of the handwritten signature, that when you sign a special document or a special message, you first of all provide the information that it is you who signed this document. So this can be verified because like the signature is linked to you. So the signature represents yourself. And secondly, the signature verifies the integrity of the document, meaning that if you change something in the document, your digital signature won't work. So if a single bit of the document changes, the signature won't verify. And this also protects from the document substitution. So if you change pretty much anything, the metadata, for example, the date of document creation or something, your signature won't verify. Which, like, not always true for the handwritten signatures. So digital signatures are like harder to break in this meaning. What about Ethereum? Ethereum uses ECDSA, elliptic curve digital signature algorithm, and actually Ethereum uses a certain standard. The ECDSA makes signatures deterministic without security compromises. So usually ECDSA is like random. What I mean is, if you want to sign something with your private key, the output signature will differ every time. But Ethereum, due to the standard, makes this signature deterministic. So if you are signing a document, pretty much every time, the output will be the same. This is achieved by providing the Ketchak 256 hash of the concatenation of your private key that you are signing with, and the hash of the message you are signing as this like entropy to the ECDSA. Yeah, to the ECDSA. Regular ECDSA uses some kind of random generator to produce the entropy, but here you're providing the seed that is always like the same in terms of the message and your private key. So this means that the output of the CDSA will be the same for this message and the private key. CDSA outputs three parameters, VRS, where R and S parameters are the parts of the signature, and V parameter is a special recovery identifier. Yeah, so if you remember, let me just quickly go back. If you remember the elliptic curve plot, we can tell that it is symmetric against x-axis. So signature can be like signature represents actually 2 points because of the properties of the elliptic curve, and in order to get like which part of the elliptic curve the signature actually represents, we have to have a special parameter, and this parameter is V parameter. It can be 0 or 1 in the like original CDSA implementation, but Ethereum adds number 27 to it, so this becomes 27, I believe, for the lower part, and 28 for the higher parts of the elliptic curve. These are minor details, but they matter a lot when you are implementing signature verification on smart contracts, and those numbers can become a hassle. Yes, and actually those numbers were simply inherited from the Bitcoin, and why are those like 27 and 28? Like there are no no known evidence. So there's just a fact, and it is hard to like understand why are those 27 and 28. Why are those not, for example, 35 and 36? Yeah, but we get what we get. And also, there is a special algorithm that ECDC provides. It is the elliptic curve recover algorithm that enables you to recover the address that signed the address that corresponds to the account that signed the message by providing this algorithm with the signature itself and the message that was signed with this signature. And if everything is okay and there are no errors, the address will be like represented, will be given. If there are errors, the frecover returns the like empty address 0. And this algorithm is available as another precompile that resides on address 1. Yeah, also used extensively, like pretty much every time when signatures are involved. Let me just quickly. Is the digital signature the hash of data? No, it is not the hash of data. It is like an output of the algorithm that uses the hash of the message as an input, but it is just a like special point on elliptic curve that you can use with some like math magic to understand which private key, like you can't understand like literally which private key, but figuratively you can use the signature to understand which private key like signed the message. So you can take the message, you can take the signature, like do the math magic with them, and it will like return true if signature and the message is correct and this message was signed with the signature, and false otherwise. So if the message is altered or the signature is altered, the algorithm will return false. But it is important that using signatures, you can't understand the exact private key that signed the message. You can understand which like public key signed the message. So there is no way of understanding the exact private key. So it is secure this way. Do we need to know the private key to verify the signature? No, you don't. Is it correct that ECDC is used for TX signing and BLS for block signing? Yeah, I will discuss that in a moment. So here is an example of the message and the signature. So what do we have here? We have a message, hello world, and we used the sign message like tab here. We connected our wallet to the website, so we provided the website with the like special endpoint where which the website could use to send the message to this endpoint. The wallet will understand that there is something to sign and return the signature. So the wallet won't uncover or leak its private key. So we have the message hello world. We fed it to our wallet, and the wallet returned the signature. So here is the signature is the long string of bytes, but actually it is a concatenation of 3 parameters. First is R parameter, second is the S parameter, and the third one is V parameter. V parameter here is the last, these 2 symbols, which are hexadecimal. They represent 28 here, and other 64 bytes are the like points on elliptic curve. About the version on the next slide. And what we have here is that we verify this message, the message hello world, and this signature. So we feed the message and the signature to the verifier algorithm, and it checks that like our account signed this message. How it does that is it calls the EC recover algorithm. It feeds the EC recover message and the signature. EC recover does its magic and outputs the address that signed the message. Then we check if this address is our address. And if it is, then everything is correct. It means that we signed the message. If it is not ours, it either means that there is an error or that the signature was altered, so the ACK recover recovered a different address. So here, everything is fine. We are sure that we are signed the message and nothing was altered. Why digital signatures are required? This is also covered in one of the next slides. If address is built from a public key, do we then use address to validate signature? So you can think of it this way, because Ethereum uses addresses to represent accounts. So yeah. Yeah, so in terms of Ethereum, you can think like that, but in terms of public key cryptography, no, it is not. Okay, so what's next? There are actually 3 standards of Ethereum signatures. The first one is vanilla ECDSA, where message hash gets signed, and this vanilla ECDSA used for signing transactions. When you're constructing a transaction, there are a lot of fields that you have to fill in. The receiver address, for example, the amounts of Ether you are sending, the call data that you provide to the smart contract. And this JSON file gets encoded with the special RLP algorithm, and you receive the encoded bytes. These bytes you sign with the via the CDSA with your private key, and you get the signature that represents this transaction. Then, when you are sending this transaction to the node recovers the address from the signature and the transaction, and by doing so, it understands who sent the transaction. So the node decodes the address and deducts Ether and increments the nonce of this account. Then there is a second type called personal sign, where the original message gets prefixed with this string. So this is the 19th byte, like hexadecimal representation. Then there is a Ethereum signed message, new line, plus the length of the message. So this prefix gets appended to the hash of the message, and then the message gets, so the out message gets hashed again, and then fed to the vanilla ECDSA algorithm. So why do we need to add this special prefix? Because in the early days of Ethereum, it was possible to scam users. So when the user logs in to your application, you can trick the wallet by providing some random bytes to sign, but actually you're providing not the random bytes, but the encoded transaction. And of course, user won't understand and decode those bytes to get what's going on. So they would just blindly sign the message, and as a result, they're signing the transaction. And yeah, so the scammer will just understand the transaction and gets all the funds the user has. So in order to mitigate this behavior, the special prefix is added to the message signed, and RLP encoding never starts with this bit. So it never has this prefix. And this is a sort of protection mechanism, so users won't sign accidentally the transaction they're just not sending. And also this enables Ethereum signatures to be used only in Ethereum, because the other protocols that are not connected to Ethereum at all, not the blockchain ones, but that use the CDSA, will not append this prefix. So the signature is going to be different. And today, wallets always append this prefix, regardless of the signature method you're calling it, except for only one case when you are signing a transaction. And the third type, it is the new one. It is called the typed sign, or more familiar EIP 712, where the message is elaborately constructed to mitigate the signature replays. This is on another level of abstraction. Here with personal sign, we tried to mitigate the problems with the transaction signing, but here we are trying to mitigate the problems of the signature replay. So what I mean by signature replay is, for example, when you are signing a message, which represents pretty much anything, there are standards like permit, which allows applications to like take your funds from your account, take ERC20 tokens from your account by signing a message. And those messages can be replayed, for example, on other chains or on other smart contracts, etc., etc. So to mitigate risks of replays, the special standard was introduced, which constructs the messages, including the chain ID, verifier contract, version, nonce, and etc., to like completely mitigate those replays. And it is used a lot today. And yeah, the usage of this like sort of new method, like you have to. So I personally recommend using it pretty much always because it is just safer. Yeah, so here is the EC recovery usage example, the one that I just talked about. So it is about the transaction recovery. Okay, so point number one, when external account constructs a transaction, there is no prompt field. The external owned account signs the transaction via their private key using a CDSA. The transaction is sent, and the signature, the VRS parameters, together with the raw transaction bytes, are broadcast to the nodes. Yes, because in order to recover the address, you have to have a signature and the message you signed. So both of those are broadcast. Courtesy of CDSA, the nodes recover the address of external account from VRS and raw transaction bytes. So they just use the EC recover algorithm and get the address. And number 5, Ether from recovered external account address is deducted to pay for gas. So why is it all safe? Because the transactions are provided with nonce. This nonce is unique for every account. So when you're sending a transaction, the subsequent transaction from your wallet will have a different nonce. So its RLP encoding will be completely different. And because ECDSA signs the hash of the message, the hash of the RLP encoding will be completely different. So pretty much it is impossible to understand what will be the next hash because, yeah, just cryptography works. Yeah, so there is a discussion in the chat, something connected with how it is possible to calculate the public key from signature. Yeah, so it is just how the signature works. So we won't go into like weeds of the CDSA algorithm. Yeah, but there are also like courses from Distributed Lab that cover in depth the cryptography. So you might also check these ones. And what about Solidity, smart contracts, and yeah, thank you. Solidity, smart contracts, and signatures. So first of all, implementing secure signature verification in Solidity is hard. There are many attack vectors to consider. It is indeed really hard because signatures are not easy. First of all, they're not easy to understand. Second of all, they're not easy to implement. And third of all, they're not easy to test. That is why when you're implementing anything that touches signatures, you have to triple verify that it works as intended. The attack vectors might be the basic like collisions when you are doing the hash of the message. So the inner message somehow may collide and the message will be like different, but hash will be the same. Also, there are replay attack vectors that are just super easy to miss. Also, if you're using multi-party signatures, like how is it called? Like protocols that require, for example, 2 signatures to do something, it is super easy to miss something there. Or you can miss some nonce verification. So yeah, this part, yeah, multi-sig, yeah, like 2 of n or pretty much anything. It is really easy to miss something there. So second point, rule of thumb is if there are signatures, they should cover the most parameters. So what I mean here is that if, for example, there is a function that users call to withdraw funds, and the validity of data and the validity that user is allowed to withdraw those funds are controlled by a third party, for example, a trusted backend, and you like provide the data, sign this data with a trusted backend private key, check that everything is okay, and smart contract uses the EC recover to recover the message, take the signature, and check if the output address is the trusted backend address. So here, this signature like should cover the most parameters, because if it doesn't, then there are ways to somehow trick the system. So if you're using signatures, cover the most parameters. Or like, if not most, then you have to be sure that it is secure. The user signatures must be EAP 712 compliant. So if there is a case in your flow, in your application, that user has to sign anything, for example, the privacy policy, when the user enters your application, you might ask them to sign the privacy policy. Or if you're placing an order, for example, OpenSea, you must use the EAP 712 standard. Otherwise, it might not be secure. The standard just like covers a lot of cases when and where the signatures might be like misused. And also some bold claim that never use the C recover precompile directly. Yeah, why never use it? And what do I mean by that? Is that the EC recover precompile accepts malleable signatures. So from previous slides, you might remember that signature contains consists of 3 parameters, the VRS. And you can so for example, signature is here, but you can flip the V parameter and take the RS point by inverse modulo of the elliptic curve. I don't remember how it's called. So the inverse modulo of the max point of the elliptic curve, let's call it like that, and you will receive the opposite signature of the one you're using. And this opposite signature is also the same valid signature. And EC recover works either with your original signature and with this flipped signature. So there are actually 2 signatures for every signed message. And what to use instead is to use a secure library, for example, from OpenZeppelin, that has a sort of abstraction built on top of the AC recover that checks that the signature itself is from the, so that it is not flipped, that the points, that elliptic curve points are from the lower part of the elliptic curve. So this is only the case when, for example, you're using signatures as nonce. So please never do like that. But sometimes protocols that don't know this logic may do so, and then they get hacked. So please use the library that mitigates this problem. Okay, so this is it for the practical cryptography in Ethereum. If you have any questions, please ask. Yeah, in this lecture, I haven't provided Solidity examples of the signature usage because they are rather hard. I believe we will cover them in subsequent lectures.
So, of course, this is not a simple topic, I think, but we hope that something has become clearer. And please wait for our quiz, our presentation, and additional links. And no, about some Telegram or Discord platform we don't have, because all of your question you can type on the classroom, in the classroom.
About zero knowledge proofs, do we have a course about them?
Maybe like additional topic, but I don't know how we can insert this topic. I think we discuss about this topic with your time. Okay.
Yes, zero knowledge proofs are really, really complex and hard to understand, and I'm also not a professional in them. Probably to understand them fully, you'll have to read some books because they are like super complex. But I believe there is a course about DeFi that covers a bit zero knowledge proofs, but not like a technical aspect of them.
We can invite special speaker from course DeFi and for this topic. Maybe. Okay. So I turn off our record.